47,000 zombie WebSocket entries silently accumulated over 14 hours. The root cause? Network-level TCP drops that never trigger WebSocket disconnect. Let's break down FastAPI WebSockets, real-time communication, how it works, and the exact mistake behind that failure. Think of HTTP as sending letters through the postal service. Each message needs a new envelope, a stamp, and a full round trip before you hear back. A WebSocket is more like picking up the phone. Once both sides say hello, you have an open line where either person can speak at any time without redialing. In production, you need a centralized structure that tracks active sessions. The connection manager pattern stores WebSocket objects in a dictionary keyed by user ID. This makes targeted messaging a dictionary lookup and broadcast a single pass over the values. Here's the Forge socket manager. The connect method accepts the handshake and stores the socket. Disconnect removes it. Broadcast uses asyncio, gather to fan out messages concurrently. This keeps latency flat regardless of connection count. WebSockets start as an HTTP upgrade request, but the browser's WebSocket API doesn't let you set custom headers like authorization. You have two options: signed query parameters or HTTP-only cookies. The critical rule: validate the token before calling accept. Here we decode the JWT token from a query parameter. If invalid, we close with code 1008, policy violation. Only after validation do we call accept. This prevents unauthenticated clients from ever being fully connected. A WebSocket connection is bound to the specific OS process that accepted it. When you run multiple Uvicorn workers, each has its own isolated connection manager. The standard fix is a pub sub-broker like Redis as a shared nervous system. Each worker subscribes to the same Redis channel on startup via the lifespan context manager. When any worker publishes a message, Redis delivers it to all subscribers. Each worker then fans out to its own local connections. TCP connections can become half-open when the underlying network disappears without sending a FIN or RSD packet. The WebSocket protocol addresses this with ping and pong control frames. The server sends a ping, the client must respond with a pong. If no pong arrives, the connection is dead. This heartbeat manager sends a ping every 30 seconds. If no pong arrives within 10 seconds, the connection is closed and removed. This bounds zombie accumulation to at most 40 seconds per dead connection. This is the same issue we highlighted at the start. Here's exactly why that happened. Mobile clients transitioning between Wi-Fi and cellular drop the TCP connection at the radio layer. No FIN, no RSD, no close frame. The server's EPAL-based event loop only wakes up when data or a close event arrives on the file descriptor. With no event, the coroutine sits parked on await WebSocket, receive text, indefinitely. Over 14 hours, 47,000 of these zombie entries accumulated, hitting the file descriptor ceiling. The server had no ping-pong heartbeat configured, so when clients dropped TCP without FIN RSD, the event loop never woke up and coroutines hung on receive text indefinitely. The immediate fix was a server-side heartbeat. Every 30 seconds, the server sends a WebSocket ping frame. If no pong arrives within 10 seconds, the connection is closed and removed. This bounds the zombie accumulation window to at most 40 seconds. We also raised limiteno FILE to 1 million and added open file descriptor count to the health endpoint. Without heartbeat logic, zombie connections accumulate in your worker's memory, eventually exhausting file descriptors and crashing the server. This is exactly the incident we saw. Always set WS ping interval and WS ping timeout in Uvicorn. If your server calls accept before validating the origin, the socket is open and consuming resources. Attackers can open thousands of sockets and leave them idle. Always validate before accept. Raw text strings are for prototypes, not production. Without a structured envelope, you have no way to distinguish message types, no schema validation, and no error handling. Use a typed message envelope with Pydantic. FastAPI's depends runs once at WebSocket Connect. Use it for handshake auth, not for per-message validation. If the user's token expires mid-session, Your code won't know unless you handle it manually inside the loop. WebSocketDisconnect only fires on a clean close frame. Network-level TCP drops, like a mobile client switching networks, never trigger this exception. The socket stays open forever, accumulating as a zombie. Query parameters appear verbatim in Nginx access logs, application logs, and any proxy. A long-lived API key and a query parameter is a credential leak waiting to happen. Use short-lived JWTs with 60-second expiry or HTTP-only cookies. A common mistake is running 4 workers and testing locally with a single client. Everything works because all connections land on the same worker. The bug only surfaces when clients on different workers stop seeing each other's messages. A WebSocket coroutine lives for the entire duration of the connection, minutes, hours, sometimes days. Each one uses roughly 48 KB of stack memory. The actual bottleneck is file descriptors. Every open WebSocket holds one OS file descriptor. The default limit on most Linux distributions is 1024, inadequate for production. Here's a production Unicorn configuration. We set 4 workers, loop for performance, native ping-pong heartbeat, and a per-worker concurrency limit of 10,000. The limit max requests is a safety valve against slow memory leaks. Every WebSocket connection starts with an HTTP upgrade request. The common mistake is assuming the WebSocket client library handles retry logic. It doesn't. You own the retry strategy. Validate the origin header before calling accept and log the client details for debugging. Here we check the origin header against an allow list. If it doesn't match, we close with code 1008 before calling accept. This prevents unauthorized domains from opening sockets. Most tutorials send plain text strings over WebSockets. In production, that's a disaster. You get one message type, no schema, no error handling. Instead, adopt a lightweight message envelope with a type field and a data payload. Here we define a Pydantic model for the message. We parse the raw JSON, validate it, and dispatch based on the type field. If the message is invalid, we send an error back but keep the connection alive. You can use depends on a WebSocket endpoint, but it only runs once during the handshake. After that, no reinjection per message. Use depends for one-time validation like auth. For per message logic, handle it inside the receive loop. Here, depends extracts the user from a cookie during the handshake. The user dict is then available inside the loop. But if the token expires mid-session, this code won't know. For production, check token freshness manually inside the loop. The article mentions using a typed message envelope, but doesn't show how to integrate Pydantic validation inside the WebSocket loop. This snippet demonstrates dispatching on MSG, type after validating with model validate JSON, keeping the connection alive for legitimate traffic. The article uses dict none for type hints, which requires Python 3.1+. If you're on Python 3.8 or 3.9, use optional dict from typing instead. This is a common gotcha when copying code into older environments. The article mentions deployment, but doesn't stress that load balancers like Amazon Web Services ALB have a default idle timeout, 60s for ALB, 350s max. Set proxy read timeout and proxy send timeout to a high value, e.g., 3600s, in your reverse proxy config to prevent premature disconnections. To diagnose zombie connections, monitor the open file descriptor count. A steady increase over time indicates a leak. Also log client headers during the handshake to identify problematic clients. Use WSCAT for manual testing. Let's run through some common interview questions. How does a WebSocket handshake work? Client sends upgrade headers, server responds with 101 switching protocols. What is the connection manager pattern? A dict keyed by user ID storing WebSocket objects for targeted messaging and broadcast. How do you detect dead WebSocket connections? Server-side ping-pong heartbeats. If no pong within timeout, close the connection. And a few frequently asked questions. Can I use depends for per message validation? No, depends runs once at connect. Handle per message logic inside the loop. What's the difference between WS ping interval and application level heartbeat? WS ping interval uses native WebSocket ping frames. Application-level heartbeat sends JSON messages. How do I scale WebSockets across multiple servers? Use Redis Pub sub as a shared message broker between workers. To recap, always validate tokens before accepting the WebSocket. Implement heartbeats to prevent zombie connections. Use Redis Pub sub when scaling across workers. Adopt a structured message protocol with Pydantic. And monitor file descriptor counts as a leading indicator of leaks. Ready to go deeper? Up next, FastAPI deployment, then FastAPI versus Flask versus Django, then FastAPI error handling and custom exception handlers. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.